Yeah, friends, in this video we'll discuss about the evaporative effect that happens in any clay refrigerator. So generally in India we'll call it as a MittiCool apparatus or MittiCool refrigerator. You can see, so the water would be placed on top of this. The water which is present at the top would try to sip or seep through these walls to the entire refrigerator, and due to the evaporative cooling effect, the food or the vegetables or fruits that are kept inside would be maintained at a low temperature. So the heat that is present inside this would be removed through evaporative cooling, and from the evaporative cooling the water vapor would be added into the atmosphere. So I'll just show you how it is. So this is the geometric modeling what I have taken for the numerical investigation inside the Ansys Fluent. So you can see this is the water and these two are the air chambers. This is air, this is also air. So sorry, so this enlarged view is present here. So the water what is present at top would seep in into the porous clay media, and then it comes down due to the capillary action, right? Now the saturation pressure condition of water vapor at the temperature at this adjacent cell. This is one cell. This cell composes of air and water vapor, and this cell composes of only water liquid. Now the water vapor fraction with 50% RH, for example, it means the mass fraction would be around 0.028 for temperature of 300 Kelvin. So there is other chance of extra 50% RH that can be accommodated into the cell which is adjacent to this wall. So that extra part is obvious. So the water liquid that is present on the other side of this clay can come and add into this cell which is adjacent to this wall, so that it can be enriched with 100%. So it has the capability to go up to 100% RH, but that cannot happen. Only partially it will be filled with that extra water vapor. So what is the driving force is the amount of water vapor present, 0.028, and other side it is completely filled, right? So now this 0.028 and it is at 100% RH, it may be around 0.04. So this is the driving force for the water liquid to leave this wall and go into the other side of the wall into the cell as a water vapor. So that is a driving force. So driving force, so mass fractions can be said as a partial pressures of water vapor. So I will say the amount of water vapor that would be added from the water liquid to the other side is proportional to partial pressure at saturation condition. At saturation condition means at 100% RH minus the right now what is the partial pressure present in the adjacent cell of the wall. It's proportional to this. So this cannot be equals to this. It is only proportional. So that proportionality constant is removed by adding heat mass transfer coefficient with the area into this driving force, Psat minus Pwv. Again, this mass transfer coefficient depends on heat transfer coefficient as well as Lewis number and Schmidt number. Okay, this how I have integrated with respect to UDF I will show you, and the area is nothing but the face area, what we are considering here, the face area. So in 3D case, this would be the face. It would have some area, right? So through this area, this amount of water liquid would leave and it will add into the atmosphere. So when it is leaving and adding into the atmosphere, what happens? So the temperature of the liquid that is present would drop because the vapor is converted. Vapor has more standard state of enthalpy. Water vapor standard state enthalpy will be more compared to water liquid. If it has more standard state enthalpy, then where does it get the heat from? It gets the heat from the water liquid. So partially, I'll again redraw here. Maybe these are the cells I'll take for considerations. But it's the mesh what I have designed in Ansys Fluent. So this is a water liquid and this is a water vapor adjacent cell. Okay, so in this cell, vapor, as it is added into this point, so there is a drop in heat content in this cell. Similarly, there would be addition of mass of water vapor into this cell. Similarly, there will be, so this is plus, this is minus, and there is also removal of mass of water liquid from this cell. Again, this is also minus. So this is the physics what we need to go and implement through UDF, such that there will be addition of water vapor here and the addition of, removal of heat from here and the removal of water liquid also from here. So the additions and removals would be in this way. This is the value through which we need to remove the mass of water liquid, add addition of mass of water vapor, similarly removal of heat from the water liquid. For the removal of heat from water liquid, we'll just try to multiply with HFG. So maybe I'll write here. So M of water vapor is equals to HM into area into Psat minus PWV, and removal of water liquid just with minus HM area Psat minus PWV, and addition of heat, removal of heat from water liquid is minus M dot water liquid into HFG of water when it turns into water vapor, right? That would be around 2246 10 power 3 kilojoule per kg. Okay, so how this I have implemented in Ansys Fluent UDF, I'll show it to you. So first I'll try to have this zone ID, which is the phase zone, right? Through that phase zone, I will have the cells which are adjacent to that phase. One is the air cells, and other is a water cell. In that air cell, I will try to calculate what is a vapor pressure with the help of this formula, and I'll also try to calculate the saturation vapor pressure at that respect to temperature with the help of this equation, right? So this equation helps us to, this can be an Einstein equation, or this can be any sort of equation which we can implement, or Thethen's equation, any equation. So this helps in giving the saturation vapor pressure at different temperatures, right? So this is the saturation vapor pressure, and this is the actual vapor pressure that is present. So difference of these two will give the driving force. And on top of this, so we need to calculate the heat transfer coefficient, which helps in giving the mass transfer coefficient. So heat transfer coefficient is given by the heat flux that is on the area divided by the temperature of the wall minus the temperature of adjacent cell where the air is present. So this gives the heat transfer coefficient. We all know heat transfer coefficient is nothing but Q is equals to HCA T wall minus T ambient, right? So Q by A is heat flux. Directly we'll get this from Ansys Fluent through the formula what I've shown, right? HC T wall minus T ambient, and HC is equals to Q divided by T wall minus T ambient. So this T ambient is nothing but the cell temperature, and T wall is nothing but this wall temperature. Okay, so that is given in this UDF. T wall minus T cell temperature of the air. With help of that, I will try to calculate the mass transfer coefficient, and I will add this mass transfer coefficient here and multiply with area with this driving force. Similarly, I will try to have another UDF or UDMI where I am having a negative sign in order to remove the water content from the adjacent cell. Similarly, removal of the heat. So I am storing all these three things in the UDMIs, which are just an open space locations where I can use those and incorporate in the mass sources of vapor. So in which here I will try to remove that mass source of vapor, mass source of liquid, and energy source, right? But this calculation I'm using in the define executed and macro, which will try to execute this loop for every time step, right? So now I'll just guide through the general setup what I have went. So this is a general, and I'm going to the transient, right? So there is a surrounding air to this wall, which I have not highlighted, because if I highlight that you cannot see anything. Maybe I'll just highlight for your convenience, and after that I'll remove. So how it exactly looks is in this way. This is the air fluid. So inside this there is a refrigerator. This is the air fluid. So when I activate that, you will be getting this extra part. Now this is the air fluid. Right now it's just adjacent to it. Okay, I'll try to activate the mixture model with implicit forces, and then I'll try to add the mixture template with water vapor and air, and water liquid as the fluid. From going to the materials tab, you can see here materials tab. In many of my previous videos I have given the setup, you can just refer. So go to create edit, and in the names I have given water vapor and air, and these are all the properties what I have taken. I have considered incompressible ideal gas because my pressure is atmospheric pressure, it doesn't changes, so my density only purely depends on the temperature. So now my density formula is ambient pressure divided by RT. This temperature I will get from the each cell, but pressure will always remain constant, which is ambient. For the air vapor mixture, not here in this area, in this area. Okay, I will close this, and now I will go to multi-phase mixture. Primary phase is water liquid, secondary phase is mixture template. In the phase interaction, I have given this surface modeling for wall adhesion, and the surface tension coefficient is 0.072. Okay, and then my phase across which the entire process should happen is this one. Display. I'm giving that phase. This is only simple phase surface. What I mean to say, across which the entire physics will happen. So that is the reason why. So this has a zone ID as 5. So I have tried to implement the zone ID as 5 here. Okay. So that is zone ID 5. Now I'll go to compile. You can just add that UDF I've already added it. You can just click build and load. So that will be come here into the console that it is loaded. Then in the function you need to add that in the executed end. Now after that you need to remove the water liquid and heat from the water liquid and add mass source of water vapor. So mass source of water vapor need to be added to this air domain. So double click this face and tick this source, and in the mass I have added this mass source vapor. As the mass is added, similarly species also we need to add same UDF or same macro, what I mean to say. Then you need to go to MittiSolid, that is again nothing but the fluid that is adjacently present to the wall. In that you will try to remove the energy by hooking this UDM macro, and after that close this. And also this is a porous media, so I have already given this porous media properties which you have taken aluminum, but you can take clay. It's only demonstration purpose. With porosity as 0.05 I have taken, and for phase 1 and phase 2 you need to give this porous properties for the viscous resistance to happen. And in this source term again I have added this mass source liquid so that the amount of water liquid would be removed from the adjacent boundary layer. Okay, so here also you need to add the same porous properties for the water liquid too. I have added that. And so there is an outflow condition what I have implemented here. I will just display. Maybe I'll need to add this one also. So okay, this is display on adjacent to this refrigerator. There is an enclosure. For all the enclosure walls have given the outflow. So any water vapor coming going will be happening on the outflow, right? And if you insert some velocity to this, so obviously the velocity from one side would increase the heat transfer coefficient, in turn the mass transfer coefficient, and in turn so there will be more amount of water vapor would be added and more cooling effect you can see. Okay, now I will try to initialize. I am trying to initialize with phase 1 volume fraction and this two with entire domain at temperature of 305, but I need to again patch this with the volume fraction of MittiSolid and this, and I will try to patch so that we will get the values. So now I will patch these values with the volume fraction for the phase 2 which is water liquid with 0, because that is the MittiCool solid, that is that porous zone which should be filled with water liquid. In the top part which is water fluid, it's also filled with the water liquid. And I'll verify. And you can see this entirely filled with water liquid and the remaining is water vapor plus air. Now I'll try to run the calculation with this particular time step size. So now I have got few results. I'll just show it to you here. Maybe I'll check with the temperature. So the temperature of this should be reduced. You can see there is a reduction in the temperature of this MittiCool box from it is 305 here, because at this there's a wall where you haven't given any mass transfer or anything, but the remaining areas we have given. So you can see the reduction in temperature clearly. It is up to 301. I have ran up to 2 seconds or 3 seconds only, right? And if you run more time it will have a much more cooling effect. Now we'll also try to visualize the velocity vectors across the plane. I'm selecting. You can see across the plane, so more amount of water vapor is added on to the different phases. So there is a air stream velocity with increased velocity, and you also can see the species which is a water vapor fraction. So you can see we have passed with only 0.023, but we are getting a 0.84 as a fraction. So more amount of water vapor is added on the mass fraction. I'll try to reduce this so that you can see evident distribution. So you can see water vapor distribution. So more amount of water vapor is added. Initially we have given only 0.023, but now you can see more than 0.023 how the water vapor fraction is added and how it is distributed as the time goes on. So there is more and more water vapor into the surroundings. Right. Hope this video helped you in understanding how the evaporative cooling would work in any clay refrigeration. Okay. Thank you. For any references or for any doubts, you can ask in the mail ID which I have dropped in description.